Okay, so now we're going to look at number 4 from MyMathLab 4.5, and I'm just going to set it up for you. This is a storage shed is to be built in the shape of a box with a square base. It is to have a volume of 125 cubic feet. The concrete base costs $6 per square foot. The roof costs $7 per square foot, and the walls cost $6.50 per square foot. Find the dimensions of the most economical shed. So let's take this apart. The number that we're given, our constraint, is 25 cubic feet. Okay, and we have a box with a square base, right? And then the other thing we're trying to do is we're trying to get the most economical shed. So that means minimize cost. That's what we're trying to do. Okay, so that's not very different. Go green. Okay. So first, let's start with our constraint. Notice I always start by finding the constraint. 125 equals, well, maybe a picture is also helpful. There's my square base. Got some walls. We're just assuming a flat roof, so we know it's a square base, so we can again do x, and y. So our constraint is x squared. Y is 125 cubic feet. And now we want to minimize cost. And so again, we're looking at surface area, but this time it's a cost. This is actually really similar to number 3, only now instead of, what were we doing there? There we were having the minimum surface area. Now we're doing minimum cost, which is similar to minimum surface area, except now the surface area is weighted by the cost, right? Cost equals area times price per area. So that's where we're going to get. So I'll just call it C. You can call it whatever you want. It doesn't really matter because we're going to take a derivative, set it equal to 0, solve for, the x or y value that makes the minimum. Okay, so let's look at the cost. Let's start with, whoa, I don't even know what just happened. Okay. Learning Notability. Okay, so the cost. Let's look at our costs. We have 6 for the base. The roof is 7 and the walls are $6.50. So let's start with the base. We have x squared times 6 plus x squared times 7 plus 4 times xy times 6.5. Okay, where did that all come from? This is the total cost for the floor. The area is x squared, the cost is 6. The second one is the total cost for the roof. The area is x squared, the cost is 7. Here we have a wall. The area is xy, the cost is 6.5, and then there are 4 of them. So that is our cost. Next thing, we need cost in one variable. So we use the constraint. The other way you could think about this is like 2 equations and 2 unknowns. Okay, so in this, I would say easier to solve for y. So y equals 125 over x squared. We put that into the cost. Cost equals 6x squared plus 7x squared plus, gosh, what is 4 times? Okay, 6.5 times 2 is 13, so times 4 is 26. X times 125 over x squared. So if we rewrite this, cost, I can put these two together since they're both multiplying x squared. So we have 13x squared plus, I'm not going to multiply, 26 times 125, whatever that is. Then we have x divided by x squared, so that leaves a single x in the denominator. Now it's very similar to the problem we just did in number 3. So you're going to find dc dx equals blah, blah, blah. You just have a couple of power rules. Then you're going to set it equal to 0 to find the minimum. You want to show, this is c prime, you want to show c double prime, so take another derivative, again, just 2 power rules. C double prime, you want to show that it's greater than 0, which is a minimum, check. And then that will give you, let's see, in there, solve for x. Show c double prime at that x is equal to 0, is greater than 0, so it's, again, concave up like a cup, so you're at a minimum. And then what? You found your x. What's the problem asking for? Find the dimensions. So you want to find x and y. Then you use y equals, what was it, 125 over x squared. You probably have a different number than 125, but whatever your number is, just, replace all of these values with your number. Okay, so again, let's look. Find your constraint. Figure out what you're trying to optimize. Use your constraint to write your optimization equation in just one variable. And once you have it in one variable, then you can take your derivative and proceed. All right, have fun.